Good morning, everyone. I'm Sushmitha Priyadarshini. Last time I spoke about roles of technology in hearing aids, and now I'm speaking about cochlear implant. When we are talking about cochlear implant, this is for the condition in which sensorineural hearing loss, whereas the auditory nerve is normal, but hair cells are damaged. So the cochlear implant is designed to bypass the damaged hair cells, and it directly stimulates the auditory nerve using electrical current. So this cochlear implant system converts the acoustic signal into electrical signal, and that yields sound or speech clarity, and it allows speech recognition skills. And all implant system works in a similar manner, where the microphone picks up the sound, sound, and it sends to the processor, where the processor sends the signal to the transmitter, where this transmitter transmits the signal to the receiver. After receiver receiving the signal, it sends to the sound passes through the electrode array, where this stimulates the damaged hair cells inside the cochlea. And this is designed features based on transmission speed, electrode design, number of electrode contacts, number of channels, and speech coding strategy. So there are two anatomical pictures, where one is depicting normal hearing and another is a cochlear implant, where the processor is sitting above the skin, and under the skin there is a receiver, and this transmits the signal along with the electrode array you can see over here, which goes inside the cochlea, the turn, and here this will stimulate the auditory nerve. It is very important to understand the hearing loss in order to choose next step. And first is age. The first year of child, in children, it's very important to develop in development of speech and language. So this hearing loss is very impactful more during this time, like during birth and after birth, who develops hearing loss soon. And the next is degree. It varies from mild to profound hearing loss, and the higher the severity, the more the impact of the hearing loss will be. So now like we are doing based on criteria, we can choose any of the age group, even for the adults with 90s, and their loss should be profound hearing loss, as moderately severe to profound. It varies according to their disease as well, any medical conditions, and their speech recognition threshold should be less than 60%, and the hearing aids will not be benefiting for them, so then they can choose the cochlear implant. So this comes under intervention, where the child is identified with hearing loss earlier stage. So then if the are chosen support services are chosen earlier, it is better for their spoken language development. And as I already said, support with early intervention, children with hearing loss who receive timely and appropriate treatment can grow and develop like others with normal hearing. The quantity of words and conversational turns a child is exposed to influences brain development, and helps develop vocabulary and academic outcomes. So during these early 5 years, first 5 years is very important for children for their brain development, where during that time the child brain will be adapting to the stimulations outside, auditory stimulations, visual stimulations, whatever it is, and they learn faster during that time, and the brain will be changing according to their learning skills. So The young children need access to millions of words and thousands of hours of listening to develop spoken language and literacy. So the more the words are stimulated, more they learn to listen and learn to speak. It's plays a major role during this time. The diversity and complexity of the language you use and how clearly your child can the child can hear it is also crucial. For children with hearing loss, sounds do not reach the brain as they should. So like since they can't hear, the sounds will not be interpreted to the brain as normal compared to normal people during based on their age. So they miss out on the opportunity to develop the neural pathways of such fundamental importance for their development. So it delays their development, or if the treatment is not done, early intervention is not taken, then the development will be very poor. So the benefits of early diagnosis and treatment of child's hearing loss are as follows. The child can undergo habilitation before the age of 6 months. The child will achieve better speech and language and educational success. The cause of hearing loss can be identified early and managed appropriately. The child's auditory system will develop better. The burden of stress within the family will be reduced. The child will continue reaping benefits in the long term, social, psychological, and educational and professional as well. So the early intervention is better. Even before the 6 months, if they go for cochlear implant, it will be much better for their speech and language develop. As I already told, the brain gets adapt to the stimulations, external stimulations like speech, um, visual, auditory, everything. The brain keeps on learning during this very first year. It's very first year is really better for their development. So why do you want a cochlear implant? So this is based on the criteria as I already mentioned. The cochlear implants can improve hearing in people with severe hearing loss who are no longer helped by using hearing aids, and the cochlear implants can improve their communication and quality of life. Cochlear implants may be placed in 1 year unilateral or both years, that is bilateral. Adults will often have one cochlear implant and one hearing aid at first. Adults may then progress to two cochlear implants as the hearing loss advances in the hearing aid year. So it's purely based on their audiograms and um, their option as well. And the cochlear implants are often placed in both ears at the same time in children with bilateral severe hearing loss, particularly for infants and children who are learning to speak and process language. So bilateral cochlear implants will be much more helpful in their binaural directionality and the speech clarity, understanding, to their listening skills and comprehension skills, speech skills, communication skills basically. Adults of any age and children who are as young as 6 to 12 months old can benefit from cochlear implants. So the people who have cochlear implants reported their improvement using like how the cochlear implant helped them. Ability to hear speech without needing visual cues such as reading lips, recognition of everyday environmental sounds, ability to listen in noisy environment, ability to find where sounds are coming from, that is directionality, and ability to hear television programs, music, and telephone conversations. So these can be heard using their extra accessories, or even direct streaming as well. Some of the cochlear implant has benefits by direct streaming without regardless of the phones, whether it is Android or iPhone. And symptoms of ringing or buzzing in the implanted ear is reduced. This has been discussed already. That is, to be eligible for a cochlear implant, one must have hearing loss that interrupts spoken communication, limited benefit from hearing aids as determined by specialized hearing tests like Pearson audiometry, BERA, etc., and motivation to participate in hearing rehabilitation and be part of the hearing world. Realistic expectations of what cochlear implants can and can't do for hearing. So the risks and complications are rare, but still, even cochlear implant surgery is very safe, as mentioned here. Um, um, while mentioning risk of cochlear implantation, one is loss of residual hearing. In some people, implantation of the device can cause a loss of any remaining unclear natural hearing in the implanted ear. So next is inflammation of the membranes surrounding the brain and spinal cord, that is meningitis. If meningitis can occur after cochlear implant surgery, um, vaccinations to reduce the risk of meningitis are generally given to adults and children before implantation, and the risk of this very rare complications is less frequent than one in 1000 people with cochlear implants. Next is failure of device. So if surgery may sometimes be needed to repair or replace a faulty internal device, this occurs in less than 5% of people over many years. And when I speak about complications, um, it may include bleeding, facial paralysis, infection at the surgery site, device infection, balance problems, dizziness, taste problems, new or worsened ear noise, that is tinnitus, and spinal fluid leak. So how cochlear implant works? First stage, the microphone picks up the sound at the level of the ear canal for the most natural listening experience, and this sound are converted into detailed digital signals by the sound processor, and the headpiece sends the digital signals to the cochlear implant and electrode array in the inner ear. And this electrode array stimulates the hearing nerve, bypassing the damaged hair cells, and the hearing nerve, auditory nerve, sends impulses to the brain, which interprets them as a sound. When sound hits the microphone, the processor receives it and it amplifies it and separates it into different frequencies with band pass filters. This band pass filtered information is sent to the inner part of the cochlear implant, where the receiver decodes the band filtered um, radio frequency signals and sends current to the electrode for the stimulation of nerves. The current generated from filtered information flows between the active and return electrodes of the cochlear implant, and the configuration of these electrodes defines the channels of the cochlear implant. Each channel has a defined bandpass filter. The transmission efficiency of electrical stimulation depends on the spacing of electrodes, stimulation modes, surface of electrodes, and distance between the electrodes and nerves. However, channel interaction due to broad spread of excitation is an inherent problem of multi-electrode stimulation. CI users suffer from insufficient spectral resolution due to interaction. Theoretically, an electrode stimulates the area directly facing it, but the electrical field generated by one stimulating electrode can cause the stimulation of neighboring spiral ganglion neurons, which is known as the spread of neural excitation. Unwanted overlaps of excitation may change the efficiency of subsequent stimuli, or if sufficient, it can trigger the firing of neighboring neurons, which leads to poor vowel and consonant recognition and poor auditory rehabilitation. Even though current cochlear implants have 12 to 22 electrodes and channels, due to channel interaction, the number of independent channels is smaller than the actual number of electrodes. Although interactions may occur between non-adjacent electrodes, they are greatest and strongest between adjacent electrodes. And for better hearing, a larger inter-electrode spacing can be used to reduce channel interactions between adjacent electrodes. The improved spectral resolution and better speech understanding are achievable with lesser spacing, lesser channel interaction. Principle of spread of neural excitation, SOE. The stimulation of electrode spreads over neighboring electrodes and causes overlapping of excitation on spiral ganglion neurons. The anatomical structure of the cochlea makes it challenging to produce cochlear implants. The main reason for this is the narrowing of the width of the cochlea towards the apex region. Due to strong channel interactions in the apical cochlea and the deep electrode insertion for optimal performance, a new design was proposed, which helped to demonstrate that larger interspacing of electrodes in the apical part decreased channel interaction and increased speech perception abilities. So as depicted by this colored scanning electron microscope image of the cochlea, there is a narrowing is visible clearly, and it limits the insertion of the electrode array into the apex region. A new electrode array with a larger interspacing of the electrode is shown in the second picture. So this picture depicts a scanning electron microscopy image of a hemi-sectioned human cochlea. Whereas this neuronal components are shown in yellow color, and green indicates the electrode array, a potential electrode positions. Some electrode designs target the electrode array to a site close to the modulus, that is perimodular lower basal turn, or at the left lower corner of the figure. While non-pre-shaped electrodes are placed closer to the spiral ligament and osseous spiral lamina, other electrodes positions. There is one electrode array which contains 12 electrodes and inter-electrode spacing is 2.4 mm. A prototype electrode array that can with a length of 26.4 mm that contains 10 electrodes. The inter-electrode spacing is 2.4 mm to 3.2 mm in the basal and middle part, and 6.4 mm in the middle and apical part of the electrode array. Longer electrode arrays with fixed number of channels provide larger inter-electrode spacing and reduced channel interaction. Although deeper insertion with a long electrode array enhances the range of place, pitch coding. Perceptual distances between adjacent electrodes are likely to decrease in the apex region. And to compensate for this, electrode array could be designed such that spacing between the electrodes in the apex is greater than the spacing between the electrodes in the rest of the array, that's basal end. And inter-electrode spacing can be classified into two groups, distantly spaced and closely spaced. So all the series of the pictures which are mentioned in the column A is distantly spaced, and in a B row it's a closely spaced electrode arrays. So there are three types of electrode arrays: perimodular, lateral wall and mid-scala. Perimodular electrode arrays, also called modulus, hugging or counter type of arrays, are placed close to the modulus wall. In this configuration, the electrode array is placed as near as possible to the modulus, which contains spiral ganglion cells, resulting in the generation of lower electrical thresholds for stimulation, higher dynamic ranges, and less channel interaction as compared to normal implant electrodes, which are usually located peripherally within the scala tympani. Next is lateral wall electrode arrays that are placed along the lateral wall of the scala tympani. All lateral wall electrodes array faces the lateral wall at an angle of approximately 180 degree, which may lead to trauma of the scala tympani. And mid-scala electrode arrays are implanted in the middle of the scala tympani, where this design minimizes trauma to the modulus wall or lateral wall, albeit with a lower quality of stimulation. So the perimodular type offers advantages over the lateral wall type in terms of um, lower stimulation levels, and expanded dynamic range and better channel separation, because perimodular configuration provides a placement of electrodes closer to spiral ganglions than the lateral wall. So it leads to better neural stimulation, which may result in better speech perception. Whereas both lateral wall and perimodular electrode array can cause intercochlear trauma, but perimodular electrode arrays are likely to deviate to the scala vestibuli from the scala tympani more often than the lateral wall electrode arrays, leading to damage of the osseous spiral lamina or spiral ligament, which can induce new bone formation and ultimately impact the hearing quality. All cochlear implants include both internal and external parts. An internal cochlear implant with an external unit attaches to the side of the head. The external unit combines a speech processor, microphone and transmitter in one device. It can be charged when needed. The sound processors, featuring enhanced technology, more accurately senses changes in the environment and automatically adjusts their hearing settings to deliver clearer sound. The sound processor continues to offer direct streaming to compatible phones, ready for the next generation Bluetooth low energy audio technology. It can make it easier to bring sound closer in more places and from more devices than ever before. Sound processing and directionality technology. Dual omnidirectional microphones work together to filter out background noise. Zoom, that is fixed directionality. This uses dual microphones work together to reduce sound from behind and to the sides to the enhance speech recognition even in noisy environments. Beam, that is adaptive directionality, reduces competing noise from several different sources in the environment and follows the prominent noise source, helping to optimize hearing in background noise. Speech in noise ratio helps provide extra support in noisy listening environment and improve speech understanding and listening comfort in steady state noise. Forward focus, that is a noise reduction algorithm that works on the dual microphone input. It is designed to more powerfully reduce unwanted background noise and focus on the speech in front compared to the previous generation sound processors. And with the option to automate or manually control control forward focus, which reduces background noise to help them focus on face-to-face conversations. With user control forward focus, microphone directionality is switched to beam, and forward focus noise reduction is at full strength. Beam is that adaptive technology, adaptive directionality. And with the automated forward focus program, the microphone directionality is also applied in different strengths to help reduce the unwanted sounds from behind. So microphones and microphone cover. Microphones we might have discussed already. There are dual microphones, triple microphones. So one microphone will be sitting on the BT processor, and the other two microphones will be on the BT processor, and the other microphone will be backside. And in some of them there are dual microphones, which where these microphones helps in picking up the signals from different directions, which is front, back, side, etc., and helps in enhancing the speech quality. And the microphone cover has been designed to protect the performance of the microphones. It is important to replace the microphone cover regularly to keep the sound processor working properly, and replacing the microphone cover every 3 months or sooner is recommended in a high humid environment. Perspire frequently if it looks visibly dirty, or they notice a loss in sound quality. Batteries and charging. The sound processor offers a tamper resistant battery lock and 3 different battery options. Typical expected battery life of 20 hours with the power extend battery module, 10 hours with the compact battery module, and a typical battery life of 35 hours using zinc air disposable batteries. The power extend battery option is similar to the standard rechargeable battery from previous generation sound processors. Connectivity. Leveraging previous generation sound processor technology, the proven benefits of streaming sound directly to the sound processor. The sound processor continues to offer direct streaming to compatible devices. The convenience of streaming phone calls, video, music, entertainment, online rehabilitation, and educational apps directly to the sound processor without needing extra accessories and cables. The sound processors are made for next generation Bluetooth low energy audio technology, making it easier to bring sound closer in more places and from more devices than ever before. There are future technology with Bluetooth or broadcast audio. Patients will be able to connect directly to what is being broadcast at public venues such as airports, conference centers, and theaters. Bluetooth low energy audio delivers better sound quality than the previous generation Bluetooth Classic in broadcast or Auracast. Smartphone compatibility. Prior to pairing, confirm that the phone is compatible with the processor. Before streaming and using the app control features, the processor needs to be paired with the compatible phones. So there are few cochlear implants that can be directly streaming without regardless of the phones, phone models like Android or iPhone. The informations are referred from the articles, certain textbooks, and Cochlear Implant Company websites.